Let's begin section 4.4, graphs of secant and cosecant functions. Now these guys are reciprocals of cosine and sine. So we're going through the whole gambit. And to understand that, we understand that chapter 4 has been about graphing trig functions. I've written down these notes and I'm going to read them to you. And again, you can put it on pause if you want to capture this outline that I've made for you. In sections 4.1 and 4.2, we graphed y equals sine x and y equals cosine x. And in 4.1, we did that. So we could figure out that the period was 2 pi. And a period is one complete cycle. Of the function. And that was because we know they repeat over and over and over. So we found out that for sine and cosine, we have a period of 2 pi. So it's inclusive, 0 to 2 pi is the domain for the period. And we know that the range is -1 to 1 inclusive because those are the mins and the maxes, the min and the maxes for the curve that perpetually cycles. Remember, it's a cycle. So then from that point, we learned that we could have the function look as y equals c plus a cosine b parenthesis x minus d, and c equals a c plus a cosine bracket b parenthesis x minus d parenthesis bracket. Now what this does is change it. We found out that the absolute value of a, is amplitude. And it is the new change in the width of the cyclical function. Then we found out that b was the period change, the effect of it. And we knew that the formula was 2 pi, which is a normal period, divided by b, whatever is multiplied by x. We found out that c was the vertical movement, up or down, depending on the sign of c, and that d was the horizontal shift of the function in the opposite sign of that plus or minus. That's what we did 4.1, 4.2. It was pretty involved. Now in 4.3, we learned about tan x having a period of pi, and the domain is parentheses because we're talking asymptotes at the endpoints of each period. And that's repeated over and over. And we had to do it because of the y, and it was an odd function. So that the range is -infinity to infinity, because those are the ratios of y over x. So remember, don't ever forget that tan of theta is y over x. So because of that condition, we're going to have reciprocal values or division of items that will create infinity to infinity, and -infinity to infinity. It is an odd function. The tan is odd. So tan of -x is equal to -tan of x. Now we come to the y cotangent of x. The period again is pi, just as the tangent. But the domain starts at, and again we're talking parentheses because we have asymptotes at 0 and pi. So it is 0 to pi. The range is -infinity to infinity. And it's an even function. It is an even function because x is in the numerator. And we're talking about quadrants 1 and 2, when we graph it from 0 to pi. And their conversion looks very similar to our sine and cosine. We have the same conditions. We have A is a multiplier of growth. It's not an amplitude, but it's a multiplier of growth. B is the period change of pi over b. C is a vertical shift of the function. That means that wherever the 0 is on the x-axis, it moves up or down by whatever C is. And D is the opposite sign horizontal shift, just the same. So now we're going to graph the secant to start with. And we need to look at what's happening. We know that the secant of any angle is going to be the reciprocal of the cosine of that angle. So we want to see what happens with some of the values. And we're going to take more or less easy ones, the quadrantals for starters, and then add to it a few of the other points. Okay, and specifically because we have conditions that will create asymptotes as well. So let's look at y equals cosine of theta. We're going to do a t-chart. And that's an x, sorry. X is radian measure, and my y is the ratios. So I'm going to start at 0. And if I do 0, I get 1. All right, that's good, right? 0, 1. Then if I do, let's do pi 6s. Then I'm going to get 1/2. All right, that's good. Then let's do pi thirds. Well, I'm going to get the square root of 3 over 2. And then let's do pi halves. And in pi halves, I get 0. All right. So let's do a few more. Let me get some. I'm not going to do as many next time. So now we're going to do, well, we will, 2 pi thirds. And we're going to get the negative square root of 3 over 2. And then we're going to get 5 pi 6s. And we're going to get a negative 1/2. And then we're going to go with pi. And we're going to get a negative 1. So we're in the positive, and then we go down to the negative. So if we have y equals secant x, and we're using the same values. All right, so we're going to get the 1. That's still what we get, isn't it? And for the pi 6, I'm going to get the 2. For pi thirds, I'm going to get 2 over the square root of 3. All right, and then for pi halves, I'm going to get, this is going to be 1 over 0, radius over value, and that's going to be my first undefined. And then I'm going to get 2 pi thirds. I'm going to get a negative 2 square roots of 3 over 3, because it's just the negative of that one. The 5 pi 6s, I'm going to get a negative 2. And the pi, I'm going to get undefined. All right, so because I'm going to get 0, I'm sorry, I'm going to get a -1. Not undefined. I got the undefined there. Now, what this does for us is give us an idea that we have undefined conditions. Well, what this means is we're flipping everything to the opposite side. Instead of a half, we get the -2. Instead of 0, we get an undefined wherever we have 0. So that would make it a 3 pi halves and so on. And we would have also the reciprocal of the larger ratio of the square root of 3 over 2 to a smaller, well, to 2 times the square root of 3 over 3. So we can see that we're getting larger numbers. So what we want to do is we want to plot our cosine. And in our cosine, we're going to use the red. At 0, we have 1. At pi halves, we have 0. At pi, we have -1. At 3 pi halves, we're back to 0, and at 2 pi, we are there. All right, so, and we're doing it like so. And we're continuing. Because it's cyclical. All right. So what this means is everywhere we had a 0, we had an asymptote. Because the reciprocal of 0 is 1 divided by 0, so we have an asymptote. We also have the flip of this of that condition. So now I have at 1 a -1 horizontal asymptotes like in algebra. Actually, they didn't call them asymptotes. They call them, well, it's okay. I'll do that. And vertical. So what we're doing is flipping. Where it is 1, it stays 1. But the others continually go down. Now you can see that it is even. It is even because we can fold at the center. And this part up here is y equals secant x. And we just did that rationalization. So we have that, and we need these guys. And then we know we're flipping them over. Now I did the 2 so that you would know that that's our 2 for the pi thirds and so on. And we'll get negative and positive on it. All right. So what are some key points to the secant line? First off, it has a period. And the period is what? What is that period for? It's 2 pi. And we have several asymptotes, don't we? So we have an enclosure from negative pi halves to 3 pi halves. We have 2 pi lengths, and it shows all the circles. It has asymptotes where cosine x equals 0. So those are the asymptotes. So that would be at pi halves, 3 pi halves, etc. on both ways, and the negative as well. There are no mins, or there is no mins. Or max values, because they go to infinity. But it's funny because the ranges are unions. They are negative infinity to negative 1 inclusive union with, then it jumps up to 1 to infinity. So we have to be careful about the fact that there is a gap because they're flipped. And we also know that it is an even function. Because it is the reciprocal of an even function, even though the outcomes are different. All right, well, there we have it. So let's look at, before we start any further, let's stop there so that you can go back and grasp some of the information. And we'll start at cosecant function.